We will continue our discussion of the model reference systems. Last time I introduced qualitative discussion, qualitative definitions of the systems. This time I want to use mathematics in order to provide numerical, quantitative description of the systems. And we will start from a model reference system that we use as an identifier or parameter estimator. We will consider a system defined using state variable notation, and we will consider specific parallel configuration of the system. The graph below shows you the real physical process. This real physical process has partially unknown parameters, parameters specifically of matrix A and matrix B. And then we have an adjustable system. This adjustable system is represented by a simulation code, effectively, that simulates a system of similar dimension using the adjustable matrices, matrix A, fundamental matrix, and adjustable matrix B. Now, both the process, and I want you to realize that in this particular application, the process works as a reference model, and the simulator works as the adjustable system. In this specific situation, the same input, signal U, is applied at both process and the simulator. Responses are different. State vector of the process is X. State vector of the adjustable system or simulator is Y. They have the same dimension, but most likely they have different numerical definitions. So we extract the error, and this error provides information to the adaptation mechanism. An adaptation mechanism, since we have a parallel configuration and since we have the parametric estimation, generates adjustments to matrix A and to matrix B of the simulator. Let's look into the mathematical descriptions. For the process, we have this conventional state variable definition with the state vector, derivative of the state vector, the fundamental matrix A, the state vector, matrix B, through which input signal affects every system state, and matrix U, and the, vector U that represents the input signal or input signals. For the adjustable system, we have derivative of the state vector Y. We have fundamental matrix that we call AS. S stands for system. Y, matrix B with subscript S that stands for system. And of course, the input signal or signals U. Error is clearly defined as X minus Y. The adaptation mechanism is the procedure that we use to change, to adjust matrix AS. And of course, it's a kind of function of error and time. So matrix S of the adjustable system is error dependent and is expected to change with time. The same we have for matrix B of the system. It is a function of error and time. What do we want to accomplish in this situation? We want the limit of the matrix A of the adjustable system to be equal to matrix A of the reference model or real process. And also, we want the matrix B of the adjustable system, defined as a function of error and time, to be equal to matrix B of the of the reference model that in our case is the real physical process. And this is supposed to happen as time approaches infinity. At this point, I will not tell you more, but you have clearly in front of you the numerical matrix vector definition of our system. The next what we will do we will consider model reference identifier or parameter estimator in state variable definition, but this time it will be a series parallel configuration. Why do we have to switch, consider in one case parallel configuration, in another case series parallel configuration? It depends on our ability to monitor specific state variables in the system. Because in this case you can see the process, which is the real physical process. It is used as a reference model. You see the adjustable system. But there are two modules in this adjustable system. So actually, there are two different adjustable systems. This adjustable matrix A is a series part of the adjustable system. And this adjustable matrix B is a parallel part of the adjustable system. How the system works? Let's take a look at the equations. For the process, we have the same state variable equation. For the adjustable system, look carefully. I have the derivative of the state vector of the adjustable system. It's equal to fundamental matrix of the adjustable system, but it is multiplied by the state vector of the process. And then we have matrix B of the adjustable system and the same input. This is why we claim that matrix B represents the parallel part of the adjustable system, and matrix A, adjustable matrix A, is a series part of the system. Now, state generalized error is the difference between state vector of the reference model and state vector of the adjustable system. Adjustable matrix A of the adjustable system is defined as a function of error and time. Matrix B is defined as a function of error and time. And what we want to accomplish is this. We want the limit of adjustable matrix A to be equal to matrix A, and the limit of the adjustable matrix B to be equal to matrix B as time approaches infinity. So the main difference is right here in the equation for the adjustable system. Equation of the adjustable system does not utilize its own state vector. It utilizes the state vector of the reference model or of the controlled process. Now I will consider with you model reference identifier / parameter estimator in the transfer function definition, and you will see first the parallel configuration of the system. Let me show you the schematics first. What you can see here is the reference model, which probably is the real physical process represented by its transfer function, that presumed to be unknown. And then we can see the adjustable system represented by its transfer function with adjustable parameters. These two components are connected in parallel because the same input raw is applied at this module and at this module. The responses or outputs theta of the process and theta of the adjustable system are compared, error epsilon is extracted, and error is applied to the input of the adaptation mechanism, and this adaptation mechanism generates the adjustable parameters alpha and adjustable parameters beta. But now let me go back and take a look at the mathematical expressions. For the process, we have this transfer function. The output of the process, theta process, is defined as the transfer function times the input rho. Well, this is an attempt to represent the same relationship using polynomials of S. For the adjustable system, we also have the transfer function, but parameters of this transfer function are alpha and beta, and these parameters are adjustable. We don't know parameters B and parameters A, but we do have the ability to monitor the output, extract the error, and so on. And based on the error information, based on the input signal, we have the ability to deploy adaptation mechanism to adjust parameters beta and parameters alpha. Well, for the sake of being rigorous, we should keep in mind that S symbol Laplace variable is symbol of differentiation. This is not that important. Those polynomials obviously are polynomials of S. They represent polynomial numerator, polynomial denominator, polynomial numerator and polynomial denominator. Theta P is output of the process, theta S is output of the adjustable system, and rho is their common input. The output generalized error epsilon is defined as this difference, and the adaptation mechanism, of course, is the function that defines parameters alpha of the adjustable system and parameters beta of the adjustable system as a function of time. And of course, our goal is to make sure that limit of every single alpha is equal to A, to corresponding value of the parameter A. Then we would know parameters A. And our goal is to make sure that adjustable betas will converge to appropriate parameters B as time approaches infinity. Let me proceed and discuss with you another configuration. It is model reference identifier or parameter estimator. It is transfer function definition, but we will be looking at the series parallel configuration. Let me show you schematics first. What you can see here is the real physical process with unknown parameters. The input is rho. The output is theta process. And then there are two adjustable modules, software modules. Look, this module is in series with the process. And this module is in parallel with the process. Now, if we will be successful in driving this error to zero, then adaptation mechanism will make sure that this module effectively will be canceling this numerator. And if this error will be successfully reduced to zero, this module will become equal to this expression with cancelled numerator. Let me go into the mathematical description. For the process, we have the transfer function. This is the definition of the output of the process, theta process. It is effectively a response to the input signal rho. This is definition of the same expression using polynomials. For the series adjustable system, we have this transfer function. Now, the input for this transfer function is the output of the reference model, theta p, or output of the process. The output of the series adjustable system is theta of the series system, we call it. You also can realize that if parameters beta are properly defined, then this series component will cancel the numerator of the process. And what will be left? What will be left is 1 divided by the denominator of the process. And that's exactly what we want to accomplish if parameters alpha are properly defined. Then this module has block. This module or this block has input rho. Output is theta series parallel. The error is defined as theta series system series minus theta system parallel. If this error will be reduced to 0, obviously we will have parameters beta equal to appropriate parameters b and parameters alpha equal to the corresponding parameters a. So adaptation mechanism is the expression defines parameter alpha and parameters beta as functions of error and time. It's our responsibility to come up with these expressions, and we will do it later. Now, the goal is making sure that alphas will converge to A's and betas will converge to B's. And of course, I want to consider with you model reference identifier, parameter estimator, transfer function definition, and it will be a series configuration. Why do we need series configuration? The choice of the configuration is important if we have no ability to monitor certain variables within the system. And from the point of view of errors, it's a long discussion, and I don't want to get into this discussion. Please take a look at the book by Landau. But from the point of view of protecting system from the effects of noise, some of these configurations are better and some of these configurations are worse. So what is happening could be understood from the schematics. This is the reference model or real physical process with unknown parameters. This is the adjustable system. However, this adjustable system is configured in such a way that if parameters alpha will be equal to parameters A, and if parameters beta will be equal to parameters B, there will be complete cancellation of dynamics of the adjustable system, or dynamics of the reference model by the dynamics of the adjustable system. And the transfer function of this path will be equal to 1. And of course, in this case, you understand why we extract the error. Error is defined as a difference between output of these two modules placed in series and the input signal. Obviously, if we are successful in estimating parameters, then the error will be equal to 0. The transfer function of this path will be equal to 1, and the goal will be achieved. And as I said, our goal is to make sure that alphas are equal to A's and betas are equal to B as time approaches infinity. Now we will take a look at a model reference control. It will be state variable definition, and we will be looking into signal adaptation. First of all, I want you to look at the system schematics. This is the reference model, but don't forget that reference model in this problem is a simulation module that has dynamics fully consistent with the design specifications for this particular system. Now, the adjustable system here is a controlled plant with a state variable controller. So I guess these components are real physical components. Now, you may ask me, where is the filter in the reference channel? For simplicity, we will assume that this filter is just a unit matrix. Now, since reference is applied to our reference model and to the control system, and properties of the control system may be inconsistent with the design specs, the responses will be different, error could be extracted, and error will be used as the input to the adaptation mechanism that will generate a special signal V. Signal V is known as the adaptation signal. All right, now let's look at the mathematics. The controlled plant has state variable notation. Please note that this is the derivative of the state vector of the controlled plant. This is the fundamental matrix of the controlled plant. This is the matrix B of the controlled plant, through which control effort affects state variables. Vector U is the vector of control efforts, or maybe just single control effort. And V is the additional signal that is supposed to force the system to behave exactly as the reference model. For the controller, again, you can see the traditional definition of the controller, except filter in the reference channel is equal to a unit matrix. U is equal R minus Fy. The F is the matrix of the controller that we use in state variable definition of the system. It's negative state variable feedback. Everything is clear. For the reference model, you have the state vector, derivative of the state vector, fundamental matrix, state vector, matrix B, and note that the input of the reference model is the reference signal. Why? Because the reference model represents the closed loop system. Error is extracted, and based on the error, we calculate define additional control signal. We call it adaptation signal. It's function of error and time. And our goal is to make sure that the state of the controlled plant, driven by its own control circuitry, will be equal to the state of the reference model. We will consider now similar system, but this time it will be a parametric adaptation. Look at the diagram. This is the reference model that represents the desired system dynamics. It most likely is a simulator in the flight control computer, for example. the adjustable system includes real physical controlled plant and the state variable controller. Now, this symbol implies that controller matrix F could be tuned, could be changed in time. All right? You may ask me, where is the filter in the reference channel? We are assuming that this filter is just a unit matrix. All right. Looking at the state variable, at the description of our state variable system, controlled plant, nothing new about controller. Reference model represents the desired closed-loop dynamics. How do we know it's closed-loop dynamics? Look, input for the reference model is a reference, because controlled plant has a different input. It's a control effort. Okay, error is calculated. Adaptation mechanism is the function, and I would say this is a quite complex function that defines controller as a function of error and time. And our goal is the same, to make sure that the state of the controlled plant will be equal to the state of the reference model as time approaches infinity. Now we will look at a more complex configuration. And I will show you the system schematics first. What to start from? First of all, I want you to see the controlled plant. It looks like we have matrix A, matrix B, and even matrix C that is used to define the output of the controlled plant. Then what you can see is the controller. Look what this controller does. This controller is represented by the adjustable controller, state variable controller with adjustable matrix F. And from the output of the matrix F block, from the output of the controller, we have a negative state variable feedback signal that is compared against reference, and we're getting the, this is how we define the control effort applied to the plant. The problem that you have to recognize is this. It looks like the state vector of the controlled plant Y is not accessible, but the state variable controller needs the state vector of the controlled plant. So what we have to do is to build a special observer, and our state variable controller receives estimated state vector Z. If you would know parameters of the controller well, if we wouldn't have the problem of incomplete information, you know how to design a state observer. We would have a great state observer and the system would work perfectly. However, properties of the controlled plant are not completely known. It's a controlled plant with incomplete information, and because of this, Z will never be a successful, never provide successful estimate of the state vector, unless we would introduce a special adaptation mechanism. What is the special adaptation mechanism? Number one, it is a procedure that is driven by error 1. And look at the error 1. Error 1 is the discrepancy between the output of the controlled plant and the output of the state observer. One output is compared against another output. We have the error extracted, and then we have the adaptation mechanism number one. And this adaptation mechanism is injected into the observer schematics. And actually it forces the observer to provide the same output as the control plant, and then we can rely on the state vector estimate z, because if this error is driven to 0, then z will be a very good representative of the state vector y of the control plant that is not accessible to us. This is one side of the story. Another side of the story is that properties of the control plant may change with time. How do we know what kind of controller we have to have for it? Design specifications represented by this reference model do not change, but properties of the control plant are expected to change, so a controller also has to change. What do we do about it? We compare the state vector of the control plant with the state vector of the reference model. And now you can tell me, look, state vector, we use state vector of the control plant. Why do we need the state observer? For one very good reason. The state vector of the control plant, if it is a realistic control plant, could be accessible several times per minute. It may not be accessible for continuous monitoring. Okay? So what we do is this. We do monitor state vector of the plant, but we monitor it with the frequency insufficient for the control problem. But this frequency is sufficient for the model reference approach. So what we do here, we have the state of the reference model compared against the state of the control plant. We do it as frequently as it is possible. Still, this is frequent enough for the adaptation mechanism. We extract the error, and we have the second adaptation mechanism that would be tuning the controller for us. So, take a look at the system. We have here two reference models. This reference model is the simulator that represents desired properties of the closed-loop system. It is consistent with the design specs. It's a simulator in the flight control computer. Now, the control plant, the control plant with its controller, is the adjustable system. The control plant, and I mark it with blue, and its controller represent the adjustable system. But then there is another model reference problem. The control plant is a reference model in the adaptive observer system. Now, control plant is a real physical system, but we use it as a reference model to adjust the observer. An observer is a module, a simulation module in a flight control computer probably, this is it. So we have two different model reference systems, two different adaptation mechanisms, two different errors extracted. Let's take a look at the mathematics. It's basically exactly what I just said. Look, for the plant, we have state equation. U is the control effort. Y is the state vector of the control plant. It looks like it is accessible, but it's not accessible with a necessary frequency. This is the output of the control plant, its output equation. And this is equation for the controller, state variable controller. You know, matrix W, we always call it W, in the reference channel seems to be just unit matrix. This is the model reference state observer. Look, it has its own equation. Z is the state vector. AO is the fundamental matrix of the observer. BO is the fundamental matrix of the observer. U is the same control effort that is applied at the control plant. And W seems to be the adaptation signal. This is the way to compute the output of the state observer. We use the same matrix C. And this is how we determine the error. It's an output error. It's a discrepancy between the output of the control plant and output of the state observer. I guess we need a reference model for these adjustables. And you can see very clearly that a reference model is the same as the control plant here. The adaptation mechanism is a complex function that defines this additional signal, adaptation signal, as a function of error in time. And I guess what? This adaptation signal forces the state observer to provide the same state vector that the controlled plant has. Except state observer, the state vector of the state observer could be subjected to continuous monitoring. And of course, our goal is to make sure that the state vector of the observer will be equal to the state vector of the control plant as time approaches infinity. And there is another model reference system. It's a model reference control system. The reference model is the model that represents the desired closed loop dynamics. It's a simulator. State generalized error is the difference between two states. State of the vector, the state vector of the control reference model, and state vector of the control plant. We have another adaptation mechanism. It's a parametric adaptation. This adaptation mechanism implements tuning of the controller, state variable controller. And of course, our goal is that the state of the control plant. Please note that this is supposed to be Y, not V. It's supposed to be Y, all right? Not V. V is the output of the control plant, but this is supposed to be Y, that the state variable, state vector of the control plant Y is equal to the state vector of the controller, of the reference model. All right, so please take a look at these notations. And again, I will make sure that this is corrected. This is the schematics that we discussed. And now I'm prepared to discuss with you some summary on the model reference principle. A model reference scheme is a mechanism that forces the response of the adjustable system to follow the response of the reference model. And I emphasize the response because in some cases we're forcing one output to follow another output. In some cases we want one state vector to follow another state vector. And the generic word for the output and for the state vector is response. Number 2. This following is achieved by the application of a special control signal, if it is a signal adaptation, or by changing some parameters of the adjustable system, which is parametric adaptation. And now you have a clear idea which is which and how their schematics look. Number 3. Model reference identification implies that parameters of the adjustable system are changed until the output matches the output of the real process. Until its output matches the output of the real process. Okay? Then it is assumed that parameters of the adjustable system properly represent the real process. And I have to talk to you about this because this proper representation could happen only under some specific conditions imposed on the signal that drives the reference model and the adjustable system. You cannot rely on this fact. What you can expect is only that the error will be driven to 0. But does it mean that parameters will be driven to their correct values? No. Unless you use a special signal, specially designed signal driving the reference model and the adjustable system. Model reference state observation, it's number 4, implies that a special control effort forces the output of the observer to follow the output of the real process. And then it is assumed that the states of the observer properly represent states of the real process. So with observer you will have much less problems than with the parameter estimation. Why do we have to not worry about parameter estimation? Because later in the self-tuning control, when I will introduce the recursive least square method procedure, you will see that there is a very good way to evaluate parameters of the unknown system. Number 5. Model reference control implies that the output of a real control system is forced to follow the output of the reference model by adjusting parameters of the controller or by the application of an additional control effort. You saw this in my schematics. The adaptation mechanism works on the error, on the discrepancy between outputs or states of the real control system and the reference model that represents the desired closed-loop dynamics. And then in one case, we generate a special signal adaptation. In another case, we have the ability to tune the matrix F of the state variable controller. Input of the reference model is the reference signal of the real control system. reference model is a simulation module in a, let's say, flight control computer. Okay? And therefore, it is well protected from external disturbances. Look, we have a system. We have our model reference system. In this model reference system, we force the state or output of the controlled plant to follow the output of the reference model. But reference model cannot be affected by its external signals, by external disturbances. But the controlled plant could be affected by external disturbances. Okay? Now you can realize that if we build a model reference control system that really works, we're protecting the output of the controlled plant of various external disturbances. The system becomes quite dependable, quite robust. It's exactly what I just said. Forcing the output of the real control system to follow the output of the reference model results in rejection of effects of the external disturbance. But, in addition, it results in the rejection of effects of internal disturbances, parameter drift, cross-coupling, nonlinearity, and so on. I did a project for the Air Force Research Lab. They had a system with 2 inputs and 2 outputs, and the system was a cross-coupled system. Okay? And this cross-coupling between dynamic channels caused difficulty in operating the system. I suggested to introduce a model reference control system. The model reference that I used was a fully decoupled system, and the adaptation mechanism forced our controlled plant to act as a reference model. So, okay, the reference model was decoupled, and the controlled plant, driven by the reference model control system, also acted as a decoupled system. It's a very good way of handling situation. And now, you also have to realize, let's say you have a multi-million-dollar controlled plant, and you have a model reference system. Let's say you want to change properties of the system and its controlled plant. You don't want to make any changes in the system. It's very dangerous to make changes in the controller of the system. You may get into instability, but what you can do is this: you can change the reference model, because the model reference approach, model reference control system, forces the real physical control plant with its control system to follow the properties of the reference model. Change the reference model, and you will observe changes in the behavior, desired behavior of the real physical system. Now, is it always doable? Is it always possible to build a successful model reference system, parameter estimator, or state observer, or control system? It depends on several assumptions. Beyond these assumptions, we cannot achieve the desired result. Mathematics that we use does not allow us to make a clear statement that the system will work or the system will not work. The justification of the successful model reference operation is possible only if some assumptions or some requirements will be satisfied. And these are so-called basic assumptions. The reference model is time-invariant linear system. Okay? We can replace one reference model by another, but we will have to redesign the adaptation mechanism then. But, generally speaking, if you build a successful model reference system, don't expect that you can change reference model and our system will keep following this reference model. As I said, you have to redesign the adaptation mechanism as well. Number 2, the reference model and the adjustable system are of the same dimension. Okay? If you have a 10th order controlled plant, make sure that the desired closed loop dynamics is represented by a 10th order simulator that works as a reference model. Issue number 3. All parameters of the adjustable system are accessible for adaptation, which implies that if you have matrix F of the state variable controller and this matrix F is to be tuned, all parameters should be accessible. You shall not be able to tune some parameters and not tune other parameters. The next issue. The initial difference between parameters of the reference model and adjustable system could be unknown. That's actually a very good statement. We don't have to worry whether we are too far from the right parameters or too close to the right parameters. This is a very good feature. And of course, issue number 7 is that state generalized error and output generalized error could be measured, because the model reference approach is based upon measurements of the error. If we do not have access to the error, we would not be able to build a realistic working adaptation mechanism. Now, there are possible practical deviations from the basic assumptions. You see, these basic assumptions enable a mathematician to provide a rigorous proof that this model reference system will work. However, there are many cases when system is working successfully, but mathematics fails to justify its flawless operation. So it happens when we deviate from these basic assumptions. Basic assumptions are needed by a mathematician. The possible practical deviations is something that engineers would surely appreciate. Number 1, the reference model is a time-dependent nonlinear system. It's good enough. It's good enough. Number 2, the adjustable system may contain nonlinearities. Number 3, the reference model and adjustable system are not of the same dimensions. This opens a Pandora box. Okay? The problem is that nobody knows the exact transfer function of a controlled plant. You describe mechanical part, but then there is thermal part, and then there are some high order effects in the system. So, mathematically speaking, true transfer function of the controlled plant has infinite number of dimensions, because everything affects real physical system. We just have to extract the principal parts of the system properties. So I guess we're lucky that in many cases, reference model and adjustable system could be of different dimensions. Not all parameters of the adjustable system could be tuned. It is something that could be easily observed in real life, but it may or may not affect performance of the model reference system. Parameters of the adjustable system could be affected not only by adaptation. Okay? In basic assumptions, we stated that there is only one input signal affecting the reference model in the adjustable system. And I guess could be some exceptions that parameters of the adjustable system could be affected not only by the adaptation. There are more than one input signals affecting the reference model in adjustable system. So some of the input signals may or may not be taken into account, and we still, in some situations, could expect successful operation of the model reference system. But you all see all these possible practical deviations, they flag particular conditions when you build a model reference system and it does not work properly. So I guess intuition, experience of the system designer is very important. State generalized error and output generalized error are contaminated with measurement noise. This could happen. Well, I guess like any realistic signal that we monitor, errors could be affected by noise. Nevertheless, I will present you the cases, the situations, the applications where model reference approach could be dependent on. And hopefully you will be able to use this skill in your practical career, in your practical experience. I'm getting into the formulation of the design problem of a model reference system. You know, we have to consider the following definition. In model reference control and model reference state observation, for any initial conditions, we can drive error to zero. It is called perfect asymptotic adaptation. This is what we expect to happen. This is what we expect to happen. It's ideal situation. When it comes to model reference parameter estimation, perfect asymptotic adaptation implies that for any initial discrepancy between parameters of the reference model and parameters of the adjustable system, we still are able of driving parameters of the adjustable system exactly to where they belong, to the parameters of the reference model. Perfect asymptotic adaptation is ideal situation. This is what we want to achieve. But I guess since we are incapable of satisfying all these initial assumptions, we may consider, we may settle on less than perfect asymptotic adaptation. Less than perfect asymptotic adaptation. In model reference control and model reference state observation, initial conditions could be within some limits, within some distance one from another. We cannot claim that initial conditions are any initial conditions, that initial discrepancy between the state of the reference model and state of the adjustable system could be anything. No. In some cases, the initial value of the error, of the discrepancy, could not be between minus infinity and plus infinity, but it could be within some limits. And as far as this initial value of the error is within some limits, does not exceed delta by the absolute value, we still can expect that we are able to drive this error to zero by building an adaptation mechanism. And I would say less than perfect asymptotic adaptation is a very common condition. Very common condition. Initial discrepancy cannot be unreasonably large, cannot be between minus infinity and plus infinity. When it comes to parameter estimation, less than perfect asymptotic adaptation implies that initial difference between matrix A of the adjustable system and matrix A of the reference model could be not between minus infinity and plus infinity, but within some limits. And in addition, the initial discrepancy between matrix B of the reference model and matrix B of the adjustable system also could be not between minus infinity and plus infinity, but within some limits. And in spite of this, adaptation mechanism enables us to drive adjustable parameters exactly to their values of the reference model. There is also a concept of less than perfect global adaptation. The previous was less than perfect asymptotic adaptation. I want you to emphasize, to realize that the word asymptotic implies that error asymptotically approaches zero, or discrepancy between parameters asymptotically approaches zero because one set of parameters becomes equal to another set of parameters. Now we will look at the less than perfect global adaptation. What does global adaptation implies? Global adaptation implies that initial conditions could be between minus infinity and plus infinity. The initial discrepancy between the state vector of the reference model and state vector of the adjustable system could be as much as possible different from each other. And regardless of this initial difference, we should be able to drive error to some small value. We may not be able to drive error to zero, but error could be guaranteed to stay within the plus minus delta limit as time approaches infinity. Model reference parameter estimation implies that initial discrepancy between parameters of the reference model and adjustable system could be virtually unlimited, from minus infinity to plus infinity, any initial conditions. However, as time approaches infinity, we may drive matrix A of the adjustable system into some limited area, into some vicinity around the matrix A of the reference model. And the same about matrix B. So I want you to appreciate the flavor of the word global. The global means any initial conditions. Any initial conditions. Asymptotic means error is driven asymptotically to zero. So obviously the best is perfect asymptotic adaptation. For any initial conditions, we have error driven to zero. But if it doesn't happen, please recognize that there are less than perfect asymptotic adaptation and less than perfect global adaptation. And then I want to remind you something about the linear negative feedback systems, which you know from my 361 class, and you know this from my 462 class. You know very well that any linear negative feedback system could be stable or unstable, period. With linear system, it's easy. However, you know that in the model reference system we have negative feedback. But a model reference systems are nonlinear by their very nature. They are nonlinear systems that have negative feedback. And since we're dealing in model reference control with nonlinear systems, the definition of stability for a system with nonlinearities is much more complex than just stable or unstable. For linear system, it's stable or unstable, but if system is nonlinear and the model reference system is a nonlinear system with negative feedback, the stability definition is more complex. First of all, a nonlinear system could be globally stable, which means if initial value of error is between minus infinity and plus infinity, the final value of error will be zero. They call it globally stable system. Sorry, I'm backing up. A nonlinear system could be globally stable. The word globally, as you know, refers to initial conditions. And globality implies that initial value of the error could be minus infinity to plus infinity. But error may not converge to zero. Error will end up, as time approaches infinity, within some vicinity around zero. Okay? Absolute value of the error at time zero is under plus minus infinity. However, the final value of the error is between minus delta and plus delta, where delta is some positive fixed number. How it happens in a real nonlinear system? A real nonlinear system may start its state trajectory somewhere in the infinity, and eventually it will converge into a particular area around zero. It may stay there, it may oscillate there, but the only what you can expect is that it will not leave, will stay permanently within this area around zero. And then a nonlinear system could be asymptotically stable, not globally. The word of globality is gone. The asymptotically stable. What this implies? This implies that for error, initial value of the error within some limits where delta is a fixed number, the final value of the error is zero. So the state trajectory of a system that is asymptotically stable eventually converges to zero, but it happens only if it is originated within some area in the state space. But of course, the best situation is globally asymptotically stable system, when, regardless of the initial conditions, the final value of the error is zero. If you say that system is just stable, this implies, and I'm talking about nonlinear system, just stable system is such a system that if initial conditions are within some closed domain in the state space, the final error will end up in a kind of closed domain around the origin in the state space. Well, stability for nonlinear systems is not global stability, and it's not asymptotic stability, and of course it's not a global asymptotic stability. So with nonlinear systems you have to be very careful. Why do we get into this discussion? We got into this discussion because designers of model reference systems decided to employ this mathematics developed for the analysis of system stability, and these mathematical techniques were developed over the last 2 centuries. It's a powerful mathematical apparatus that was never fully utilized until model reference control was introduced. So what do we do in the model reference control? The design problem of a model reference system we interpret as the design of a globally asymptotically stable system, or globally stable system, or asymptotically stable system. Why? Because we want to utilize all this powerful mathematical apparatus to solve the design problem. Okay? This treatment allows for the utilization of powerful stability analysis methods that have been developed for nonlinear control systems over a long period of time. And at this point, I exhausted material prepared for today, and I can stop my recording.